Lesson 11.3, multiplying matrices. Now, we're talking about multiplying matrices. We're talking about multiplying two matrices together. And there's a little tricky process to this. It's not as simply a scalar multiple. Like before, you guys saw if you say multiply 5 times an entire matrix, you just multiply each element by 5. You cannot do that when you multiply a matrix by a matrix. But before I even dig into the examples, I want to show you guys say like a practical application of this so it's not completely abstract. And so here's a physics application of this called a cross product. And so let's say you want to use this wrench to turn this nut. Maybe it's rusted over and you have to press really hard, right? So how do you loosen this, right? Or if you're opening a door, this nut could be the place of the door hinges and where you're pressing over here on the opposite end of the wrench. That could be the door handle, right? If you like that better, right? So how can you get this to turn? Well, I think if you press harder, that'll help it turn better. Oh, how about if you increase this radial arm, this distance? Like if you could somehow extend the length of the wrench or widen the door, right? Ooh, hey, maybe that's why the door handle is opposite of the hinges, right? Like if you put the handle over here, or in the case of the wrench, if you pressed over here, that'd probably be more difficult to get this to turn. Okay, so if you increase R, if you increase F, but one more detail, which is I have to multiply just the perpendicular components. So the physics version of this with torque, this sine theta as an example, right? Like for example, if you pressed parallel to the door, if you or the wrench, the door or the wrench, if you press like parallel to this R, that would never turn it, right? And if you want to get the maximum turning moment or torque, then you'd want to press perpendicular. Okay, this is called a cross product. And when you're multiplying matrices, you could see represent this radius as a matrix value and this force is a matrix value in 2 dimensions. So you'd have these two-dimensional matrix values and then multiply them together with matrix multiplication. If you ever come across this is another way to look at cross product. You might run into this in a college level class. So you just plant this image right here. All right. And then uh, the value of that torque, like how much torque do you get? Another way to look at this is see like how what if you were to find the area of this parallelogram, the area of this parallelogram, right? Like again, to give you guys an example of the directions of these things, right? If you pressed a force that was parallel to this radius, then the area of this parallelogram would be zero, and you would also get zero torque. That sounds like it goes hand in hand, right? Or if you press this force like exactly perpendicular to this radius, which is not quite shown here, but if you did, then this parallelogram would actually turn into a rectangle. And I think that would maximize the area of that parallelogram if it was a rectangle. Right? And it would also be maximizing the torque, the turn moment to try to get this rusty nut to turn. Right? Or how about in 3 dimensions? What if you want a 3 dimensional example? Because you guys are going to see some 3 by 3 matrices. So what if you want to go like X, Y, and Z, or here it's called I, J, and K. Same idea, right? But if you had some crazy 3 dimensional system, right, you could press in any 3 dimensional direction and this wrench would be oriented however. Okay? Now, you guys see these bars here? Like at a glance, okay, it looks like a matrix, but wait a minute, that's not quite because those aren't brackets. Those are like straight bars. This is called the determinant. So the determinant, you can think of it as telling you the area of this parallelogram, or in 3 dimensions, it's sort of like a slanted boxy shape. Has a name to it too. Um, they can tell you the value of well torque in this case for the physics example. Okay, and let's browse around a bit on YouTube. There's this channel called Three Blue One Brown. It has a lot of good math examples. So here he's talking about the determinant of a transformation. So he's looking at the area of this. Well, it starts out as a square. Now maybe this could be like 0, 0, 1, 0, 0, 1, and 1, 1, right? If those were unit values, right? And then, okay, how could you twist that here? I'm going to mute this and just let the animation play here. All right, we got the scaling factor, these column determinant, right? So, wait a minute, am I getting ahead a little bit? I think I am. Yeah, sorry guys, I think this is actually the next next unit. So I'll come back to this, but maybe I'll plant this idea here, right? Right, so you can, yeah, all right, you can see it here. All right, so eventually we'll get into determinants, right? And then I think I got a 3 dimensional example here. Yeah, yeah. Oh, there it is. It's called a parallelepiped, I think it was. Okay, slanty cube. Where is it? There it is, parallelepiped. All right, so we got that. All right, so that's actually getting a little bit into the next lesson. but maybe you can see those visuals and think ahead a little bit. All right, so let's get back over to just simply multiplying matrices. All right, so we're going to multiply these matrices together. All right, so the tricky thing here is, let's say you got matrix A and matrix B, right? Now, if they're showing a little dot here, if you go to college, they'll probably more likely show a little X for what's called a cross product, right? Cross product. Sometimes this book simplifies some things, and this is one of those examples. So I have this matrix A, B, C, D here, and this other matrix E, F, G, H. So they're both two by two matrices. Right? But what's the product of multiplying those matrices? So you have to do AE times BG. Okay, so that will be the first element of the product. Okay, okay, so do you see how I'm going across the row on the first matrix and down the column for the second matrix? Okay. What you might be thinking, if you're thinking ahead a little bit, is that this multiplication process is not commutative. What that means is if I multiply matrix B times A, I would actually get a different answer. Usually, you usually do, or you can. Right? Okay. How about all these other ones? Okay. So what if I want the top right one? Okay. Element. So I can go AF times BH. Is that what they did? Yep. There's AFBH. Right. How about the bottom left? Okay. So I go CE times DG. There it is. CE DG. And finally CF DH. Okay. Now that's for a two by two matrix. If you stretch your imagination a little bit, you can probably go into three dimensions with this. I think eventually we'll see a 3D example. Okay. But interestingly, to even multiply matrices together at all, you need them to, okay, you need the number of columns on the first matrix and the number of rows on the second matrix to match. Okay, so if you have a 2 by 3 and a 3 by 4, you would be able to multiply those together. Okay. And interestingly, the product would have numbers of rows and columns equal to number of rows of the first matrix, number of columns of the second matrix. Okay? So as we go through some examples, look for something like that. So say if you had CD, this is a 3 by 2 matrix and another 3 by 2. Well, 3 by 2 and 3 by 2, this 2 and this 3 are different numbers, therefore you cannot multiply them together. Okay? So you aren't even allowed to multiply those matrices together. Okay? All right, let's get to this example here. So I'm gonna write this down on paper so it looks bigger. All right, so I got matrix G is defined as 1, 3, 8, -4, and matrix H is defined as 5, -2, 9, 4. Okay. Okay, and it looks like they're looking for GH. So what is GH? Got a 2 by 2 and a 2 by 2. So I'm going to say it's equal to, right? Now I should get some answer that's also 2 by 2, right? So I'm going to go 5 times 1 plus 3 times 9. So 5 times 1 plus 3 times 9. Okay, so that will be the first element of the product. Okay, now how about this second element? Okay, so 1 times -2, 3 times 4. 1 times -2 plus 3 times 4. Right? Then down here, I got 8, 5, and -4, 9. Okay? So 8 times 5 plus -4 times 9. And finally, down here, we got 8 times -2 plus, and then, okay, -4 times 4. -4 by 4. All right. So let's simplify this a bit here. This is going to be, well, 5 and 27, I think it's 32. Is that right? 32. Yeah. Got -2 and 12 should make 10. I got 8 times 5, that's 40. That's 4 times 9. So, okay, so overall this comes out to 4. And then this is -16 minus another 16 should be -32. Okay, so that should be that one right there. All right, and let me show you guys that if you multiply the other way, like G times H, you're probably going to get a different answer. Okay, so let's try it, or HG and HG. Okay, so that could be, let's go back to the top here, and I can play out these. Okay. Well, this time, and I'll go ahead and write it out. Right, got 5, -2, 9, 4, and that's multiplied by 1, 3, 8, -4. There you go. Okay, so I have H here and G here. Okay, so this is equal to Okay, I got 5 times 1 and negative 2 times 8. 5 times 1 plus negative 2 times 8. Right? And then 5 times 3, negative 2, negative 4. 5 times 3 plus negative 2 times negative 4. And down here, got 1, 9, and 4, 8. 1 by 9 plus 4 by 8. And finally, got 9 times 3 plus 4 times negative 4. All right, so let's clean all that up. I got 5 minus 16 is negative 11 here. You got 15. Now two negatives cancel, so you just say plus 8 gives me 23. 9 plus 32 is 41. And 27 minus 16 is 11. All right, so that right there is HG. See, if I go back to what I did before with GH, it's a totally different result. Okay? So again, doing a cross product of matrices is not commutative. So GH and HG actually come out to different results. Yeah. All right, let's see what we got next here. Um, okay, so we did multiply square matrices. So we can do that. Uh, multiply rectangular matrices. All right, so we got a P and a Q. Right now, I'll copy those down. Got my flip this off screen here. Okay, so we got P equals, we got negative 2, 3, 0, 1, 5, negative 1. And Q equals, we got 6, 2, negative 4, 8, 9, 10. Okay. Now P is a 2 by 3 matrix, 2 by 3, and Q is a 3 by 2. Okay. So can you multiply these together? Yes, because the number of columns here and the number of rows here matches. So I can multiply these together. And the answer is going to be a 2 by 2 matrix, 2 by 2 if I do P times Q. Now, if I did Q times P, I could still multiply them together, but it would give a 3 by 3 as a result. Maybe I'll do that later. So let's do PQ equals. So I should end up getting a 2 by 2 here. Let's see. All right. So let's do 2 times, or negative 2 times 6, that's negative 12. Plus 3 times negative 4 is another negative 12. Plus 0 times 9, which is 0. Okay. Then over here, I get negative 2 times 2, it's negative 4. 3 times 8 is 24. And 0 times 10 is 0. Then down here, I got 6 minus 20 and minus 9. And then finally here, I got 2 plus 40 minus 10. All right. So let's see, put this all together. Well, that's definitely negative 24. This is 20. What's 6 minus 20 minus 9? Negative 23 and 32. Yeah, there you go. There's PQ. That's PQ. What if I did QP? What would that look like? And I'm going to get a completely different result. I should get a 3 by 3 matrix for QP. Let's see if I get. So QP would be the 6, 2, negative 4, 8, 9, 10. So there's my Q right there, right? There. Right, and then I cross multiply. Whoops, I got negative 2, 3, 0, 1, 5, negative 1. There you go. There is my P. All right, so there's Q, there's P. Straight out. Again, I should be getting a big old 3 by 3 going on here. Yeah. Because I recognize that this is a 3 by 2 matrix and this is a 2 by 3 matrix. Yes, I'm allowed to multiply these together because the number of columns here matches the number of rows here. Okay? If you look at these outside numbers, rows and columns, that's what's making me think I'm going to get a 3 by 3. So let's do 6 times negative 2 is negative 12. Okay. Plus 2 times 1 is 2. Boom. That's that element right there. That's it. Okay. Moving on. Let's go to the middle. 6 times 3 is 18. 2 times 5 is 10. 6 times 0 is 0. 2 times negative 1 is negative 2. All right. Next row. Negative 4, negative 2 is positive 8. And another 8. Right. negative 12, and 40. 0 and negative 8. And last row, we got negative 18 and 10. I got 27 and 50. I got 0 and negative 10. So clean this up a bit. All right, so that's definitely negative 10, 28, negative 2, 16, is that 28, I think? And negative 8. And then negative 8, ooh, 77 and negative 10. Yeah, so there's the answer for Q key. Okay. And so just to recap, PQ turned out to be a 2 by 2 matrix. Q key turned out to be a 3 by 3 matrix. Yeah. All right, next one. Okay. Looks like one more main example, so this should cover this. During lunchtime hours, Sunnyside Cafe offers 3 specials as shown. We got 4 large group tables order the lunch special shown in the table. Okay, so we got table A, table B, table C, table D. And we got these 3 specials, and then how many specials, but how many tables. Got it all in this matrix. These matrices to determine the total bill for each of the group tables. Total bill, right? Oh, and here's the prices of the specials, prices of the specials, right? All right, so let's see, I have a 4 by 3 table, 4 by 3. And the pricings are 3 by 1. So if I want to multiply them together at all, the only way to do it is this matrix times that matrix. Because again, it's not commutative. So if you tried it the other way, you wouldn't be able to multiply it. You can't do a 3 by 1 times a 4 by 3. But you can do a 4 by 3 times a 3 by 1 in that order. Okay, so let's do that. And we'll see that. And the answer is going to be a 4 by 1. Oh, you know what, guys? Since the answer is going to be a 4 by 1, that could represent the bills of the 4 tables. Okay. Okay, so great. Right now we're taking a story example and we're applying this matrix math to it. So we got straight from the book. We got a 2, 6, 5, 4, 8, 3, 6, 5, 1, 0, 3, 8. Okay, we're gonna multiply that by, so a little cross product there. We got $9, $11, $12. Right, just to show you. Yeah, okay, because those numbers look maybe a bit abstract, but right, they come from this table which tells a story. Right? And so we've got these 4 different tables. We've got these 3 different specials, and we have the prices of the specials. Okay? So think ahead a little bit here. If I have yeah, got special 1 times the price of special 1, and special 2 times the price of special 2, and special 3 times the price of special 3. Yeah. So as I multiply using matrix multiplication, the prices will correspond to the bills that they applied to. Yeah, so that'll be perfect. That'll work out. Okay, so that's equal to, and I should be looking for a 4 by 1 matrix. So maybe something like this. Well, yeah, makes a little bit because I'm adding up a bunch of these. Okay, let's go 2 times 9, which is 18. These are all in dollars, I guess. They're all in dollars. 6 times 11, which is 66. And 5 times 12, 60. All right, so that's for special, or sorry, that's for table A. Okay, that's the bill for table A. So bill for each table. That's the way I'm going to interpret this. All right, these are the prices, and these are, well, number of specials ordered at each table. There you go. Okay. Well, labels there. Okay, how about table B? Got 4 times 9. I got 8 times 11. And 3 times 12. Table C. Got 6 times 9. 5 times 11. 1 times 12. Table D. 0, 33, 96. Okay. So equals. All right, and then this is the same. just consolidate it a bit here. Okay, what is 18 plus 66 plus 60? Okay, so table A paid $144. You guys see these will all be dollars, so go ahead and put dollars back in. And it was 36, 88, 36. It's 160. 54, 55, and 12 is $121. Okay, I say it is $129. There you go. Right. Right, that's the bill for each table. Yeah, so if you're bringing them up in the back, then $144 to table A and so on. Yeah. All right. Well, that's all the examples, and that should cover any question you get out of that lesson.